This video is part of a series in which we step through the design of a microcontroller core in System Verilog. In this first video, we'll go over the design of the ALU. The EveCore architecture will require an ALU module. This will be completely combinational. In other words, there is no internal state. There's only inputs and outputs. For inputs, we'll have two 8-bit values, which we call A and B. These will end up coming from the A and B registers, but we don't need to worry about that now. And it will produce one 8-bit output, which will ultimately feed into the A register. So this little cross sign here is indicating that there are 8 parallel wires. And here we have the function code going in, and that's 4 bits. These will be the exact same codes that the instruction, the ALU instruction itself, uses. In addition to producing an 8-bit output, it will also produce values for the carry, sign, zero, and overflow flags. And these will be used to set the condition codes whenever an ALU instruction is executed. The shift instructions also require a carry in, and the add with carry and the subtract with borrow, which is sometimes called subtract with carry, also requires the previous value of the carry. So we need to have an input called carry in. So next, let's take a look at the Verilog code for this functional unit. Here's the module for the ALU, but before we talk about that, let's define the function codes. So we define 16 different values, and I'm specifying them in decimal, but hex is just fine. These correspond exactly to the function codes that will appear in the ALU instructions. So we see the logical operations, we see the add and subtract operations, we see the shift operations, and increment and decrement. Okay, now let's take a look at the module. We begin with the interface to the outside world. We have some inputs, including the A input, the B input, and the 4-bit function code, and the carry in. And so these are the input wires. And then for the output, we have exactly what was on the picture. We have the 8-bit ALU output, that's the A out. And then we have the carry out, the sign out, the zero out, and the overflow out. The little O here indicates output. We will have some logics, if you will, which is Verilog, for a sort of a wire that we can use in an always comb construct. And so we have basically one for each one of these things. Here's the ALU out, the carry out, sign, zero, and overflow out. And all we are doing here is assigning to each of the actual outputs one of these values here. And so from here on out, throughout this module, we'll be focusing on these, and you could ignore the ones that start with O underscore. We compute some temporary results or some results combinationally for the addition and subtraction. And the overflow formula for addition and subtraction is rather complex, so it's also pulled out. So here we're computing the result of the addition, and we see an assign statement here where we are taking the input value and the of A and B, and we're adding them together, and maybe we're adding in the carry. That's what's going on right here. So we ask whether the function code happens to equal add with carry, and if it does, we're going to also add in the carry input. And if it doesn't, well, we just add in 0. In other words, we don't add the carry. The carry is 1 bit, so Verilog will, of course, extend this to the appropriate number of bits. But notice what we've done here. These, the A and B inputs are 8 bits from 0 to 7, but our result here is 1 more bit. It's 9 bits. And this will give us our carry out. The 9th bit is actually the carry out. So the 8-bit result will be from 0 to 7, and the last bit, the most significant bit, will be the carry out. Now, I'm not going to go over the formula for overflow right now. but it's covered elsewhere. But well, basically, I can say that we're looking at the sign bits of the A and B inputs, and we're looking at the result, the sign bit, the 7th bit of the result. Okay, and if A and B are positive, for example, if both of these are true, then it better be the case that the result is also positive. Okay, so if it's not, then that would be an overflow. And likewise, we can see that if the A and the B input are negative, then the result had better not be positive. And if it is, that would be an overflow situation. Okay, here's the formula for the subtraction, and it's very similar. We're subtracting A minus B, and then we're possibly subtracting the carry. So here we are saying if the function code indicates the subtract with carry instruction, then we would subtract the carry input, otherwise we subtract nothing. And again, the subtract result is a 9-bit value. So we're subtracting two 8-bit values and producing a 9-bit result, and that 9th bit is the borrow. And so we're going to be using that for the carry output later. And the formula for the overflow in the case of subtraction is somewhat similar. Of course, you can, with subtraction, we're basically negating the B value. So you can see that the formula for the first formula for the add overflow is the same as the subtract overflow, except the sign of B is reversed. And then the second formula for the overflow is the same as the second formula for the overflow in the add case, except the B sign is reversed. And so these formulas give us the results for the add and add with carry and the subtract and subtract with borrow functions. So now let's go ahead and take a look at the bulk of the ALU function. Normally we would like to use an always comb construct, but we're going to be testing this using the EDA playground, and I found out that it doesn't seem to like that, and so I'm using this older form here instead. But if you're not using EDA playground, you should probably just code the always comb keyword here. And we've got to begin and then all the way to the bottom. And you know, this is the entire module. It just does all the cases, and then that's basically the end of it. Now, I like to put assignment statements at the beginning here of all the variables that I want to be assigned in this. Okay, we don't want any latches being accidentally created. So I'm going to go ahead and initialize things. And all things being equal, the condition code outputs will be 0. But in certain cases, we'll modify that. And I also set the ALU out, although I'm careful to do every single case. And in every single case, I will set the ALU out. And so that doesn't end up having any impact. And of course, it would be optimized away when we synthesize this. But the AND function, so we're going to do a big switch statement on the 4-bit function code. And so here you see all the different cases for our different function codes. And I'm doing them in order. The logical operations are pretty straightforward. We will leave the condition codes unchanged. And for the AND operation, we simply use the Verilog AND operator to produce the output. For OR, we do OR. And for exclusive OR, we use this Verilog OR operator. And for the NOT function code, we just negate the bits. Now, I should add that at the end of this combination, always comb block, at the end of the case, we are going to set the sign output and the 0 output. So after this is all done, if you want to look at it like that, we will send out of the ALU the most significant bit of the result, the ALU out result, as the sign bit. That is the sign bit, so we will just copy it to the output. And for the 0 output, we are testing to see whether the result turned out to be 8 0 bits, and if so, the 0 flag should be 1, so we output a 1, and if they're not equal, then we output a 0. So for all of the possible function codes, the sign and the 0 outputs will be set. For many of them, the carry will be set, or the overflow will be set, but in some of them, those won't be set, and they will just take their default values of 0. So after looking at AND, OR, exclusive OR, and NOT, let's scroll up and look at the add. We've already computed the result, so we just grab the lower 8 bits of the 9-bit result, and that becomes our output value. And then we grab the most significant bit as the carry bit and send that out. And then we've already computed the overflow, so we grab that, and that's the overflow output. The add with carry is a very similar thing. I should say it's an identical thing. There's that. And then we have the formula or the cases for the subtract function and the subtract with carry function. And again, we grab the 8 bits of the subtraction result, and that's our output. And we look at the most significant bit as the carry output, or I should say borrow in the case of subtract. And we output that. Notice we output the carry output regardless of whether we're using the input or not, the carry input or not. And likewise, we set the overflow output. And then we have an increment and a decrement function. And these just add 1 or subtract 1. And we don't involve the carry in any way or the overflow in any way. And then we have the clear function. And so that just moves zeros into the ALU output. And I have a blank line there for some reason, which I need to get rid of. And then for the negate function, we are basically negating the bits in the A input and adding 1. That's how we form an arithmetic negation of a signed value. And the carry is not involved in any way. We don't bother setting the carry. And the overflow, though, we will set. There's only one value that cannot be negated, and that is the most negative value. In hex, it would be 80. That is value with the most significant bit set to 1. And if we negate that, we get the exact same thing after we add 1 to it. So if our input happened to be that, we set the overflow flag. Otherwise, we don't. Now we have the shift functions. So here we're using the Verilog notation with the braces, and we're basically grabbing 7 bits, the least significant 7 bits, and we're moving them over a little bit by 1 bit, and then adding in a 0 here. And for the shift left with carry, we're shifting in the carry input value. And in both cases, we're setting the carry output to the bit that got shifted out, namely the most significant bit of the A input. For the shift right functions, we are doing more or less the same thing. We're taking the 7 most significant bits, and we're putting a 0 on the left end here, and that gives us our 8 bits that we're copying into the output. And we're setting the carry to whatever was previously in the least significant bit. And for the shift right with carry, instead of shifting in a 0, we're shifting in the carry input value, but otherwise it's the same. It's a good practice, I suppose, to always include the default case. So I've handled all the possible combinations for the function code, but I've included a default case here just in case. Okay, so now we want to go ahead and test this thing. So we need to create a test bench. So now we're looking at the code from a different file, and this file contains the test bench. The ALU is fairly complex. It's got a lot of input combinations. You know, there are 8 plus 8 plus 4 plus 1 bits of input. That's a lot of combinations. And we need to test this thing thoroughly. If we have a bug in the ALU, then it's going to be difficult to deal with later. If you've got a core that's running but it has a particular bug in the ALU, it's going to be really a pain to try and figure out what's going on. So it's important to test this thing thoroughly. And in the course of testing the ALU, I did find a couple of mistakes that I had made. So it's well worth the trouble. So we start off in this file with a repetition of the function codes, which we'll be using. And then we have the module to act as the test bed for the ALU. Okay, here is where we include or instantiate an ALU module. I'm just calling it my ALU. And we see the inputs and the outputs. And I've defined some registers for the function code, the A, the B, and the carry input. And those are used in the module. They're fed to the module. And then I have some wires for the outputs. So you see that for each of the various outputs, there is a corresponding wire. And in the case of the result, it's a bus of 8 wires. Now, there are just a jillion combinations that we want to test. And so I've created a task, which I call do test. And we're going to use that over and over. So if I just scroll down this file, you can see that there's a lot going on here. And it goes on and on and on. We're testing lots of different things. So let's see what happens. First of all, we're going to display something that says that this test bench is running, and then we're going to wait for 1 clock cycle. And then we run through the various tests. First, we're going to test the AND function. And so I am invoking this task right here with the do test call, if you will. And I've kind of labeled things in this comment so you can see what I'm passing to this task. First of all, we have an 8-bit input for the A, and then an 8-bit input for the B, and then we have the function code, and then we have the carry input that I want to test. And let's see if I can scroll over here a little bit. And the arguments here provide the desired output, the expected output. I'm going to look at this task in a little bit, but I'm passing it what I expect the output to be, along with the carry, sign, 0, and overflow outputs. And so you can see for an A input and a B input, well, the most significant bit is a 1 in both of these, so the output should have a 1. And the least significant bit is a 0 and a 1, so it should be 0. And you can work through all of these and see that they do test the AND condition. Now, when you're making test data, you really want to test everything. You want to test the most significant bits and the least significant bits, and pretty much any bits in between. Obviously, we're not going to test all the possible combinations. But here I'm testing the carry in different situations and verifying that I get the results that I expect. There are a couple where there's a 0 output, and some where the sign is set and some where it's not set. And I do the same thing for testing OR, exclusive OR, and NOT. And then at this point, let's shift down to the bottom of the file and look at this do task so we can see how it works. So let me just scroll down here through all of the different tests. Now, I should add that in some of these tests, for example, for testing the subtract function, I'm providing the inputs in decimal just because binary was driving me crazy. But in either case, it's 8 bits, and so it doesn't matter whether you specify it in decimal or not. Okay, so let's go down here to the task. After we're done with all the last tests, we display a message that says the test complete, and then the test bench ends. So we should get some nice output from this thing. The do test task will also produce output. So we'll see what's going on. We'll see the tests as they run. And so this do test has all of these inputs, and they're repeated here. The A, the B, the function code, and the carry input. And then we have the desired results, the desired output, and the desired carry, sign, zero, and overflow outputs. And I want to display these values both in hex and in signed decimal notation. So I've got a couple of registers here for the input in a signed version, the A and the B input in signed version, and I've also got the output from the ALU in a signed version. And then Verilog allows you to have strings, or at least in the test bench, and those are useful for creating a pretty display. And so I've got one string that is going to be the function that we're executing, so we can see that. And so based on the function code, all right, the test function code that's being input, the one thing that we're trying to test, I set string to a character string that has something that's human readable here. And so that sets up the string variable. And then I have a similar one for the operation because I'm going to be printing out the addition. Addition and subtraction were a bit tricky, so I wanted to print them out in decimal. And so I print out the operation. So if it is an add or an add with carry, it'll be a plus. If it's a subtract or subtract with carry, I'll print out a minus sign. And for the others, I don't really care about those, so I just print out X's. Okay, so now let's stimulate the ALU module, if you will. So the ALU module has A, B, function code, and carry in wires. Okay, and so let's go way back up to the top, and we see where we instantiate our module, A, B, function code, and the carry in. And so we are setting those to whatever this test is going to be. Okay, those are registers, so we're going to set those registers with A, B, the function code, and the carry in. And we've also got these registers for the sign. Okay, I don't know if I mentioned that, but A signed is a register, but it also has the signed keyword, and that is important. I did that because I want to print these things out in decimal, and when you print this register out, if it's assigned, it'll print out with the proper sign on it, plus or minus, and otherwise it would print out as unsigned. So we're doing that. So here we set up the A signed, B signed registers, and then we wait one cycle, and that allows the ALU to do its thing, and at that point the ALU output has been produced. So we clock it into the ALU out signed register, and then we display things. Okay, so this display is pretty ugly here. Runs over several lines, but we are displaying what the inputs are. And we're displaying what the outputs are, and then we display it in decimal notation. Okay, so more precisely, we're specifying, we're printing out what A is and what B is in binary. Then we're printing out our function code, both in decimal and as assigned, as the string value. So we can see the string value, a representation that makes sense. And then we're displaying the output, and we're displaying what carry goes in, and then we're displaying what carry comes out, as well as the sign out. And going down to the next line, the zero output, the overflow output. And then we are displaying the operation. In the case it's an add or subtract, this is relevant. Helped me debug all of this and see what was going on. So we're displaying it. First we're displaying this, a string, and then decimal numbers. So 3 decimal numbers with the string. And that would be the A in decimal, unsigned, the operation, that is plus or minus, or XXX, and then B, and then the output. And then we're doing the same thing again over here. We're displaying the decimal, 4 digits for the sign symbol, and the operation, and then the result as 4 decimal digits. And so you're seeing that displayed here, A signed, the operation, B signed, and the ALU out signed. Okay, so then what do we do? After we display that line, we then check to make sure that this thing was what we expected it to be. So here we are checking the output that came out of the ALU against the desired output, and the carry output, the sign output, the zero output, and the overflow output. And if any one of those is not equal, then we've got a problem. And so we display, and basically we display a bunch of stars so I don't miss it by accident. And then we display what the desired results were. Up here, we're displaying what the actual output from the ALU was, and if it doesn't match, then we display what the desired output was, so we can begin to try and figure things out. And then finally, we have the end of the task and the end of the module. So then we can run this thing on some kind of a simulator, such as the EDA Playground, which is a free simulator, and see what the output is. It's critical that we test our ALU module to make sure it's working, and so we need to run the test bench. And to do that, I'm going to use this EDA Playground thing. This is a free website, so I've already created a little login and gone to the website, and this is what you're presented with on this website. So if you've got access to something more sophisticated like Model Sim, then that's probably a better option, but this is free. One thing we need to do is go down and select which simulator we're using, and I'm selecting one of the free ones, Icarus here. Earlier I said that the EDA Playground didn't accept the always comb construct, but I think it's actually Icarus that has the problem with that. But in any case, let me show you how this thing works. It's got 3 windows up on top here, or 2 windows up on top, here and here, and we paste into the test bench window, and I've already done that. This is exactly the code that I just got done going over. And then on the other window, I've already pasted in the code for the ALU module that I presented. So then let's go down here to the bottom window. We'll click the log, and that's where our output will be displayed. And then if we go back up here to the top of the window, we can go ahead and select Run, and then it is running, and pretty soon it produces a bunch of output. So let's go down and take a look at this. And we can see, well, we go all the way back up to the top, and it prints the message, and we can see that for, let's look at the add, for example. We can see the inputs. This is a function add, and here's our output in binary. We're providing, in our particular test case, no carry, and we're getting a carry out, a sign out, and so on. And let's see, I've got some issues scrolling this, so let's see if I can show you the far side of this. And here we see the data displayed first as unsigned numbers. So we can see that this is perfectly good as an unsigned addition, and it's also perfectly good as a signed addition, but we're displaying the values in signed form as well. Here we can see a situation where we are adding two numbers and the signed addition is okay, that's fine. But when we view these as signed numbers, then there's an overflow. Okay, so the unsigned version is okay. And we have other situations as well, as for example, here we're overflowing 8 bits, and we can see that the carry output is 1. And so we can then scroll through all of this output, looking for those errors, and we see no errors. And so it looks like our ALU is working, and this thing ends by printing the test complete message. And so we're ready to move on in the design of the EveCore with a working ALU. I'll see you in the next video.